Now that we fully understand exponential functions, right? We're ready to move on to their inverse log functions, logarithmic functions. Now, think about what we know about inverses. To be a function, we have to pass the vertical line test. To be a one-to-one function, you also have to pass the horizontal line test. And we know that's important because every one-to-one function has an inverse that is also a function. I can invert anything, but for that inverse to still be a function, my original function has to have started out one-to-one. Well, what does one-to-one mean? It means that each x value is assigned a unique y value. And the graph of a one-to-one function is going to passes both, should be passes. A one-to-one function passes both the vertical line test and the horizontal line test. Exponential functions are one-to-one functions. Therefore, their inverses, logarithms, are also functions, logarithm functions. How about that? Logarithmic functions. I'm having trouble with the English today. Sorry. The grammar. How do I find the inverse of a function? We're going to use that switch and solve test to find the inverse of a function. You switch out the x and y, and then solve for y again to find the inverse function. What do we know about inverse functions? The three characteristics. We know that those two functions are going to reflect across that line y equals x. So if we have an equation, we use switch and solve. If we have a graph, we reflect across that line y equals x. Another thing we can do with a graph is to exchange the domain and range so that the x value becomes the y value and vice versa. For example, here, my original function has the point 1, -3. Therefore, that inverse function has the point -3, 1. Those x and y values switch place. So if we have our function, we use switch and solve. If we have a graph, we use one or both of those two characteristics to get our inverse function. So let's look at our parent exponential function, base 2 of x, base 2 to the x, and then we're going to find its inverse log function, base 2. What do we know about our parent exponential function? Well, let's color code this. Let's do this in green. When we're doing our exponential functions, we're going to use those magic 5 values to help us find the asymptote, that horizontal asymptote, and our exponential increase or decrease. I'm raising 2 to that power, so that's going to be 1/4, 1/2. Anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4. So we have 5 ordered pairs that we can put on our graph. That y-intercept, 0, 1. And then we've got 2 to the first is 2. 2 squared is 4. And we've got our exponential increase. That is f of x equals 2 to the x power. Now, our exponential function has a domain of all real numbers. Our range is limited by a horizontal asymptote. You'll notice I did not put my horizontal asymptote in here. That's because hopefully we're comfortable with that and we are focusing more on that log function. But our range is limited by that horizontal asymptote, not inclusive 0 to positive infinity. That's our range for our parent exponential function. Now let's think about our line of reflection, y equals x. So that line is going to go straight through the origin, the slope of a positive 1. That's my line of reflection for any function and its inverse. Now things I know to do. I know that the function in its inverse, here we've got this one in green, we're going to do our log base 2 in red. I know that my domain and range are going to switch places. I know that that means that this point on my exponential function, 0, 1, becomes the point on my log function, 1, 0. And I know that I can switch the domains for my chart. So these those magic 5 values for my x become y values. They're not really magic, they just make things easy. And then my y values become x values. And I can plot these 5 points. Well, this one is already plotted. My y-intercept becomes my x-intercept. Then I'm at 2 and 1, 4, 1, 2, 3, 4, and 2. There's that curve that matches the curve there. Instead of a horizontal asymptote, I now have a vertical asymptote. So my exponential function has a horizontal asymptote at y equals 0. My log function has a vertical asymptote. Let's stick with my colors. Sorry guys. My log function is in red. My log function would have a vertical asymptote at x equals 0. Because log functions and exponential functions are inverses of each other. Now this is a really important piece of information down here as we are working with log equations. The answer to my log function is always the exponent. If I'm solving a log function, the answer is going to be the exponent. Now what does that mean? Let's go ahead and look at our definition for logarithm. A logarithm function, base a. Now remember, our exponential function was also base a. This corresponds. So f of x equals log base a of x, where x and a are both real numbers. Now we have those two restrictions, right? I have a third restriction. So the two restrictions that I already know from exponential functions. I know that base is going to be positive. It's going to be greater than 0. And I know that it's not equal to 1 because that gave me my constant function. The other thing I also know from my log function is that x is going to be a positive value. Because if I raise a positive value to an exponent, the result is always going to be positive as well. Now when I'm working with log and exponential functions, I'm going to use that definition of logarithm right here to switch back and forth. Okay? There are 3 pieces of information that switch places when I convert from an exponential function to its inverse logarithmic function and back. Now what are those 3 pieces of information? Well, let's start with an exponential function. Let's think 2 cubed equals 8. So let's think 2 cubed equals 8. There's an exponential function. That's 3 pieces of information. My base is that 2 right there. That's my base. The base goes down low when I'm writing it in log form. So that's where the base would go. Then I have an exponent. This 3 is my exponent. And remember on that last page, what did we say about with a log function? That the answer to the log function is the exponent. And that is equal to an argument. In exponential form, base raised to an exponent is equal to an argument. That argument goes on this side of my log function. Log base of the argument, and then the answer is that exponent. So, over here, this same example, log base 2 of 8 is equal to my exponent 3. So I just took these same 3 pieces of information and rearranged them to put them in log form. And I realized a while ago that my pens on my desk make a lot of noise, and I'm sorry about that. I don't have a good solution for that though. Okay, we're going to practice. remember that when you are solving a log problem, your answer is going to be that exponent. That's what you're looking for. You want to identify the base raised to some exponent is equal to an argument. So let's think through this. Right here, I would say log base 3 of 9. That's how I would read that. Log base 3 of 9. And my answer is going to be the exponent that would make this happen. So if my base is 3 and I have some exponent, then the argument is 9. What is that exponent? Well, 3 squared gives me 9. That's my missing exponent. Same thing here. My base is 2. I've got an exponent that I'm missing. My argument here is 1/4. Well, how do I change 2 into 1/4? Well, 2 squared is 4, right? But how do I take that reciprocal? Negative exponent. So anytime I see a fraction as my argument, think negative exponent. All right, how about my base here is 1/2. I want to know what exponent I raise that to, and I can end up with 8. I'm looking again for that exponent. Well, think through this logically. 2 squared is 4. 2 cubed is 8. If I just do 1/2 cubed, it would be 1/8. So again, I need to throw in that negative exponent to take the reciprocal. So when I see a fraction here, what do you think? I'm thinking negative exponent, right? 4 to what power is 16? Well, 4 squared is 16, but it needs to be 1/16. So there's where my negative exponent comes in. All right. What is the exponent of 2 that gives me a -4? Now, I want us to think about this a little bit. This -4 is my value x. Is there a power, an exponent I can raise 2 to that's going to make it negative? If I go back to my definition, that argument, it has to be positive because my base starts positive, my argument also has to be positive. So this is not possible. That just does not work. Make sure as you're thinking, as you're reading through these problems, that you think about it and see if it makes sense. Don't get in a rush. Right here, base 3, some exponent gives me 0. What power can I raise something to and get 0? Well, is that a thing? Can I raise something to a power and get 0? I know I can raise it to the 0 power and get 1, but no, this does not exist either. This is not possible. There is no exponent I can raise something to and get 0. I can say does not exist on these instead of saying they're not possible. Just make sure that you reason through, that you don't just go in and get a hurry and not think your way. Make sure you are reasonable. Now, all of our graphing, we are focusing on transformation. So we are going to take this log function base 2, and we are going to use some transformations on it. Now, on our first page, we already did this. This is how I want you to always start. If I ask you to graph a log graph, start here. Start with the inverse exponential function, get your ordered pairs, and reverse that domain and range so that you know what to graph for your log function. So we started with this exponential function, created this list. Here's my list that I created by starting with my exponential function. And I did not just pull this out of thin air. If I hadn't done it already on a piece of paper and been able to look at it, I would have started here on my homework. So these are my points. I've got 1, 0, I've got 2, 1, and 4, 2. That means that this is my curve, it's an increase, this I'm approaching, and I need to sketch in my vertical asymptote is part of my graph. X-intercept is part of my graph. Those two things are definitely parts of my graph. Now I need to answer all of these questions. I have a vertical asymptote. The equation for that vertical asymptote is x equals 0. The domain of my function is limited, 0 to positive infinity. The range of my function is all real numbers. It has an x-intercept at 1, 0, and it is an increasing function. So I've answered all the questions for this parent function, base 2. Now, and I want you to make sure that as you go through these on homework and on written assignments, that you read the instructions carefully. First, sketch the parent function, then do transformations to graph g of x. Parent function. There's my intercept. There's my parent function. That's my parent function f of x. Okay, now that it is sketched, I'm going to look to see what g of x has for me. G of x has a negative out front. If I go back, if I need to, I go back to my pattern of transformations, and negative out front tells me I'm going to reflect across the x-axis. If you just say reflect and you don't tell me where, we've got a problem. I'm going to have a vertical asymptote. Now, the vertical asymptote for my parent function goes right here. I have not moved that. So that vertical asymptote is still at x equals 0, which means my domain and range have not changed. My x-intercept is going to change, though, because instead of being 1, 0, I flip across that x-axis. Oh, I just flipped the wrong way. So glad I caught that. I flip across the x-axis. My x-intercept does not change. What changes is that now the tail, as it approaches the asymptote, is going up, and my curve is coming down. So this is g of x. And if you don't have more than one color, make sure that you do dotted lines, label, whatever you need to do. So my intercept stays the same. It's still at 1, 0. This function, though, is decreasing. It changed directions, and now it's a decreasing function, not an increasing function. All three of these problems on the next page are still base 2. They still have the same parent function, so let's start by sketching that parent function. My parent function has that intercept at 1, 0. Quick sketch. That's my parent function f of x. Okay. Now let's think about this. Log base 2 of negative x. We've got a negative in a different place. That negative is not out front. That negative is on the side. So what does that do to me? Well, it reflects the other way. That one's going to reflect across the y-axis. That's what I started to do a while ago. Since I'm reflecting across the y-axis, I'm not moving my vertical asymptote. Now, if I reflect across the y-axis, it's like it's in a mirror, so it curves back this way. My domain has changed. Instead of being 0 to positive infinity, it has turned around, and now it's negative infinity to 0. Make sure you always go least to greatest. My range, anything that starts all real numbers, stays all real numbers, that will never change. My x-intercept changed. Now it's negative 1, 0. This function, if I travel from left to right, is a decreasing function. All right, number 4. Now, number 4 and 5, I really want you to pause the video, try it on your own, and then come back to see what I've done. All right, let's see. There's my transformation. It's inside attached to the x. It started out as x minus 8, so I'm going 3 units to the right. So I'm taking this intercept and I'm shifting it 1, 2, 3 units. There's my new x-intercept at 4, 0. And I can, you know what, I'm going to go ahead from instead of 0, I'm going to mark in my vertical asymptote because it did change this time. And that helps me guide where this tails down. There is g of x. All right, still have a vertical asymptote because it's a log function. It has moved over 3. So now my vertical asymptote is at x equals 3. Make sure you do the whole equation. That domain has a new limit. Instead of the limit being 0, the limit is the value of that vertical asymptote, the new value of the vertical asymptote. Range Once it starts all numbers, it stays all real numbers. Doesn't ever change. X-intercept changed, and it is an increasing function. So I'm not just following a set of steps. I am reasoning through what I know about the functions and what I know about my pattern of transformations. That moved me to the right. This one is going to move up. All right. So I'm taking this shift up 3, so I'm going to move that intercept 1, 2, 3. When I move it up, I'm not moving anything left or right, so this vertical asymptote stays where it is for the parent. X equals 0, sorry. Which means my domain is still limited at 0. Range, all real numbers, is always all real numbers. I've shifted up 3 units. That means that it still follows that same path. X-intercept, so increasing function, that's easy. Got to do a little work for that x-intercept. I know that x-intercept is going to be between 0 and 1, but I don't know what it's going to be. I would definitely have to do some work for that, and I haven't given you the tools for that yet, so let's just be between 0 and 1. How about that? Okay. Last page of notes. Let's see what we've got. All right, so we did our graphing bit. We talked about what the graph of our logarithmic function looks like. We compared it to the graph of our exponential function. Now let's talk about working with some log functions mathematically. Log functions have a limit on our domain, right? We've got, if you look at these that we have over here, our domains have limits. Wherever our vertical asymptote fell, that was where we had a limit on our domain. So log functions are going to have limits on our domain. And that limit is going to show up changing. Sorry, I just shifted through these. I'm going to shift back. It's going to show up a change on my domain when I have an expression inside parentheses. It's not just x, it's x plus or minus something. That's going to let me know I have a new limit on my domain, and I need to think about where that has gone. Now, keeping in mind that for both exponential and log functions, that base a is restricted. A is going to be positive, and a is not going to be 1. So those are some limits that we've got. Because of this, therefore, dot, 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 in triangle, therefore, my argument is also going to be positive. It's going to be greater than 0. So let's look at this expression in parentheses and see what that has done to the restriction on my domain. I'm going to take this and I'm going to say, okay, that needs to be greater than 0. So let's solve. Let's subtract the 2. So I've got negative x greater than negative 2. Now I need to divide both sides by a negative 1 to finish solving. And when I divide by a negative 1, that reverses that inequality symbol. So now I've got x less than 2 as my domain. What does that look like? Well, if I stick that on a number line, x values less than 2 are over here. So my domain is from negative infinity up to not including 2. I've turned and I'm headed back the other way. That negative x in there means I've reflected across the y-axis. Okay, so those are 2 ways to write that answer. 3 ways with a number line. All right, let's do this next one. Look at that expression and say, okay, what keeps that greater than 0? Well, I add that 5 to move it over, and I've got x values greater than 5. So if my limit is there at 5, I'm going from 5 greater, so my domain is 5 to infinity. And same thing here. Take this expression out to see what I've done. see where that's greater than 0. X values have to be greater than -2. Greater than -2 for my domain. So I've shifted it back 2 to the left, 5 to the right, reflected it across the y-axis. That's how those domains change. All right, last thing we're going to talk about in our video today, how to use your calculator to work with logarithms. There isn't an any base button on your calculator. You have 2 special bases on your calculator right there, common log and natural log. And if you can't remember which is which, that second function up above tells you the base. Common log is base 10, natural log is base e. So your 2 special bases on your calculator, common log is base 10, and it's my LOG log button. Natural log is base e, and remember e is an irrational constant, and that's my LN button. E is approximately 2.72. All right, simplify. This first set, we're going to do it without using your calculator. They're common log, which means they're base what? Well, common log is base 10. So I'm asking my question, what is the exponent? What is the exponent on 10 that gives me 1,000? Well, I've got 3 zeros, so that's 10 cubed. Which makes this one 10 to the 5th. And this one, I've moved it the other way. I've got tenths, hundredths, thousandths. I've got 10 to the something equals 1,000. Well, 10 cubed is 1,000. 1,000th is going to be -3, reciprocal power. How do I know these are all common logs? Well, it's LOG log with no base written. Now these next 3 are natural logs, and I know these are all natural logs. How? Well, it is LN with no base written. So I understood that it's natural log. Now with common log, I said to do it without your calculator. This one I say, okay, you gotta use your calculator because E is an irrational number. So you're gonna do natural log of 1, and you got 0. Anything to the 0 power is 1, that makes sense. E to the something is 1. This one would be E to the some exponent is 10, and remember E is 2.72, so that's not going to be a nice number. It says in my instructions to round to 3 decimal places if needed, so I'm going to do natural log of 10, sorry for the glare, natural log of 10, 3 decimal places is needed. I get 2.303. And then this last one, natural log of -6, be sure you use the negative and not the subtraction button. Domain error. Why does that give me a domain error? Well, this bit of information is my argument. And what do we know about our argument? Because our base is positive, our argument is also positive, so that is outside my domain, which means this logarithm is undefined. Doesn't exist on our graph.